Okay, so I think maybe we can begin now.
Okay.
Okay, sure. Yeah, my apologies for the delay. So, hello everyone. Let's welcome Ms. Dipanjali, today's speaker. So she'll be talking on quantum algorithms for the ground state energetics of strongly correlated molecules. I'll just talk a little bit about her and then she can begin. So Ms. Dipanjali did her bachelor's degree in science from Presidency University in Kolkata and her master's degree from IIT Bhubaneswar. So she's currently a doctoral student at IIT Bombay, and her research interest is in quantum algorithms and for the ground state energetics of strongly correlated molecules. So yes, Ms. Dipanjali.
Okay, thank you very much. So shall I share the screen?
Yes, please. Yes.
Okay. I hope it's visible.
Yes, yes.
Yeah. Okay. So good afternoon, everyone. So the topic of my presentation is quantum algorithms for the ground state energetics of strongly correlated molecules. So before diving deep into the quantum algorithms for simulating molecular systems, let me just briefly talk about the basic building blocks of quantum computers. So the first one is the qubits, which are the basic unit of quantum information, which are basically the quantum analogs of the classical beats. So any two-level system, like the spin states of an electron or the polarization states of a photon, can be considered as a qubit. And secondly, the quantum gates, which are the quantum analog of the classical gates, except for the fact that quantum gates are reversible in nature, unlike the classical gates. Since the quantum gates are nothing but unitary matrices, so by construction, they are reversible in nature. So now the question is, can we simulate molecular energetics using quantum algorithms? Okay, so till date, there are various classical algorithms that actually serves the purpose. Like the full configuration interaction, the FCI, is an exact theory because it spans the n-electron Hilbert space in the spaces defined by k-spin orbitals. So it's an exact theory, but it comes at the cost of an exponential scaling against the system size. Whereas quantum algorithms like the phase estimation technique is capable of performing an FCI calculation with polynomial scaling. So now let me talk about what quantum phase estimation is. Now, the basic objective of the quantum phase estimation technique is to estimate the eigenphase corresponding to an eigenvector of a unitary operator. So the unitary operator in our case is e to the power minus IHT, as shown here. And we generally write down the energy eigenphase as a series of binary digits, as shown here. We have written down the phase eigenphase phi as 0.5152, so on and so forth. This phi 1, phi 2 are binary digits. So now the precision of the algorithm is basically so we want to estimate the phase to a desired degree of precision. Now this degree of precision is basically pre-decided, and that depends on the length of the binary beats that we use to expand the phase. Also, the length of the binary beats basically dictates the number of iterations required to estimate the phase. Now, not going into the mathematics, let me just show a very basic and a very simple quantum circuit for the phase estimation algorithm. Well, I call this circuit the basic and the most simplest because we have restricted ourselves to calculation of eigenphase till only the first decimal place. So we require only one ancilla qubit. So as you can see, in the bottom towards the left hand side, we have an ancilla which is initially in state 0. And we have just below that, we have an initial state denoted by chi reference. So chi reference contains as many qubits as is required to define the initial state of the system. Now, what I can say superficially without going into the details is that through a series of various basis changing operations, like through Hadamard operations and controlled evolution operations, the phase corresponding to an eigenvector is kicked back onto the ancilla, so that when we measure the ancilla, we can read out the corresponding eigenphase of the eigenvector. Okay, so can you see my screen?
Yes.
Oh, okay, thank you. Okay, so now here is a small example where I have taken the initial reference state as a linear combination of 3 slated determinants. So it's just an example. So here we have taken a linear combination of the ground state chi0 and the 2 other excited states, chi1 and chi2. And the corresponding eigenphases has been mentioned on the right-hand side by alpha naught, alpha 1, and alpha 2. So the aim is to determine the ground state eigenphase to a given degree of precision. Now, this degree of precision to which we want to measure or estimate the phase is basically pre-decided. So in our case, we have restricted ourselves to 3 iterations. So the length of beats that we'll be able to measure is 3. So how this algorithm works is that first, the least significant beat is estimated, and then the second least significant beat is estimated, so on and so forth. And at the end, we measure the most significant beat, phi 2. So not going into the details of the circuit structure, so I can say that at each iteration, we basically narrow down our search algorithm. So we narrow down the probability of reaching the undesired higher eigenstates, so that at the end of the final iteration, we end up with the target ground state. Through a little bit of mathematics, we can show that the probability of extracting the phase corresponding to the target state, which is ground state in our case, is square of the coefficient, that is C0 square. So it is worth mentioning at this point that the initial state preparation is of utmost importance for the success of the phase estimation algorithm, because more closer the initial state is to the target state, more is the probability of hitting the correct target state. Since the algorithm is probabilistic in nature, so there are chances that the phase estimation might take us to some undesired higher excited routes. So we need to maximize our chances of reaching the correct target state. So we can do that by preparing our initial state in such a fashion that it has maximum overlap with the target state. So one of the very basic and the simplest choices for initial state is the Hartree-Fock state, but it suffers from a drawback, which is it works really well for the single reference region, but it fails in the strongly correlated region. So I can show this. So we have taken H4 on a circle molecule, where 2 H2 molecules are placed on a circle, and we vary the angle between them. The angle is denoted by beta. So at beta towards 80 degree, the region is a single reference region. But for beta towards 90 degree, it's a strongly correlated region. I have shown the qubit representation of the Hartree-Fock state for H4 on a circle in the STO3G basis also here. And now to test if phase estimation leads us to the correct eigenstate, if we start from the Hartree-Fock state, so we have done a phase estimation experiment 40 times for the H4 on a circle molecule starting from the Hartree-Fock state. So here, as you can see in the plot, and this IQPE has been done for beta equal to 89.8 degrees, which is basically a strongly correlated region due to the presence of quasi-degenerate states. And here, as you can see that each of the blocks carries 40 dots. So this 40 dots basically denotes the 40 repetitions of the phase estimation experiment. And on the x-axis, I have written down something called 25 shots, 50 shots, so on and so forth. So by shots, what I mean is that I am repeating the beat measurement 25 times, 50 times, 100 times, and 10,000 times. Now, with such a scenario, if we do a phase estimation over the Hartree-Fock state, then we see that all the time we reach the excited eigenroot. So the color of the dots falls in the orangish reddish region, which basically denotes an excited eigenroot. And we have plotted and we have also marked the EFCI, that is the FCI exact energy, which comes in the greenish bluish region. So we can see that starting from the Hartree-Fock state, it is never the case where we are going to the correct eigenphase. So now we have come up with an algorithm to using the already known variational quantum eigensolver algorithm to maximize the success probability of our initial state. So before going into the details, let me just talk a little bit about the variational quantum eigensolver algorithm. So it's a hybrid quantum classical algorithm where the quantum part of the algorithm deals with preparation of a parameterized state based on the choice of an answers, and the classical part of the algorithm deals with optimization of the expectation value of the Hamiltonian till a global minima is reached. But for our case, we don't need a fully optimized state from VQE. We need a semi-optimized state from the variational quantum energy eigensolver algorithm. So what we do is that we take a semi-optimized state from the VQE algorithm, which is a multi-determinantal state, and we feed it into the phase estimation algorithm as an initial state, so that when we measure the ancilla at the end, we get the phase beat associated with this correlated state, ground state prepared by the VQE algorithm. So for our VQE algorithm, state preparation via the VQE algorithm, we have considered a unitary operator, which is of this form, e to the power T2 minus T2 dagger, where this T2 are nothing but two body excitation operators. So this is the unitary couple cluster doubles operator. And through various mapping schemes like Jordan-Wigner transformation or Bravik-Kitaev transformation, we map the operator into the second quantized operators into a series of Pauli gates or the unitary gates to get the multi-determinantal state for our phase estimation technique. And what we can see is that if we look at these graphs, on the x-axis, I have marked number of variational quantum eigensolver iterations, and on the y-axis, I have marked the success probabilities of the initial state, that is the state that we prepared using VQE, with the target state and the excited eigenstates. And what we can see is that for number of iterations 0, which basically refers to the Hartree-Fock state, the success probability or the overlap of the initially prepared state with the excited states and the target ground state are almost same. So that's why starting from Hartree-Fock state is not a very good option. But if you see, if we increase the number of iterations, VQE iterations, we can see that the success probability between the initially prepared state and the excited state diminishes to 0, whereas the success probability between our initially prepared state and the target ground state reaches almost equal to 0.95. So we can see that via the VQE algorithm, we can prepare a multi-determinantal state which has a very good overlap or substantial overlap with the target ground state. And now with such a multi-determinantal semi-optimized state, we have performed a phase estimation calculation, and we have drawn the potential energy surface with our scheme. And what we can see is that the IQPE over VQE curve and the FCI curve are parallel throughout the potential energy surface. It is worth mentioning at this point that the final precision of the energy estimated by the QP algorithm is independent of the initial reference state. But a reference state with a very high overlap with the ground state largely enhances the probability of extracting the correct ground state eigenphase. Now, we have again conducted 40 quantum phase estimation experiments starting from a variationally prepared state. And what we observe is that all the times we reach the greenish bluish region, which is basically the correct eigenstate. So now we aim to reduce the cost of initial state preparation. So what we do is that we choose only a subset of T2 operators rather than taking all the double excitation operators. So our answers now looks something like this, because we only work with the excitation operators that are defined within the active orbital space. So we end up with two dominant configurations. One is the Hartree-Fock state, and the other one is a doubly excited determinant, which where the excitations take place within the active space, that is the orbitals nearby the Fermi level. And with such a minimally parameterized answers, we have again conducted our quantum phase estimation experiment 40 times again. And what we observe is that all the time we reach again the correct eigenphase. Hence, we can say that with a shallow gate depth, with a minimally parameterized answers that have a much shallower gate depth than the full space answers, we can reach the correct eigenspace. So here are the summary of the resource requirements for the state preparation. Now, as we can see that the minimally parameterized answers scales sublinearly in terms of both parameters count and gate count in comparison to the full space answers. And also it leads us to the correct target state. So we can say that the minimally parameterized answers actually maintains a right balance between a shallow gate depth and the accuracy. Now, the phase estimation algorithm is exact, but due to the use of controlled evolution operators, it leads to a very high gate depth, and it goes beyond the reach of the near-term quantum devices. So now the question is it possible to simulate molecular systems at a much lower implementation cost? So now we have tried working with the variational quantum eigensolver and tried to improve the answers or come up with the better answers that can take care of both the single reference and the strongly correlated regions at a much shallower gate depth. So we all know that the choice of a parameterized answers plays a very crucial role in the performance of VQE. So the key aspects of a good answers is that it should be able to span the n electron Hilbert space, but at a small gate depth, at a less gate depth. But mostly an expressive answers comes with a huge circuit depth. So we have come up with a double unitary answers that basically maintains a right balance between the requirement of less gate depth and the expressibility. Now, before going into our newly developed answers, let me talk a little bit about the most widely used chemically motivated answers, which is the unitary coupled cluster answers. So, if we include the higher excitations, then with the UCC answers, it starts scaling hugely. So in order to circumvent this problem, we have taken into account two body operators, which are the S operators and the T operators. So by S, I mean a scattering operator. So scattering operator has two vertex. So one vertex consists of a real excitation from the hole to the particle region, and another vertex consists of a scattering in the hole region or in the particle region. So using this double unitary answers, I can show that how we can mimic the effects of higher body excitations, but our operators are two body operators. But using these two body operators, we can mimic the effects of higher higher rank excitations. So here is an example. Say we have a Hartree-Fock state, and we let a two body operator act on the Hartree-Fock state so that we get a doubly excited determinant as shown here. And now if our S operator acts on this doubly excited determinant, then we end up with a triply excited determinant. It's just an example, so I have shown a triply excited determinant, but via the contractions of S and T operators, and due to the exponential nature of the answer of the e to the power S operator, it is possible to simulate the effects of higher rank excitations using only two body operators. So we have written down the S and T unitarized versions of the S and T operators here, and we again do a mapping to convert these operators into the qubit basis, and our wave function answers looks like this on the left hand side in the bottom. So we have first all the quantum gates corresponding to the S operators, which necessarily acts on the entangled states produced by the e to the power T operators acted on phi Hartree-Fock. Now we also further repeat our answers, make repetitions of our answers so as to get better accuracy and precision. And here is the detailed circuit structure where the T operators acts directly on the Hartree-Fock state, and the S operator necessarily acts on the entangled states produced by the T operators when acted on the Hartree-Fock state. And then we perform a coupled optimization to update the variational parameters in order to get the VQE energies with our answers. And these are the various approximations that we have used to scale down to reduce the gate count of our answers. So I have listed down our various variants of the answers in the decreasing order of the number of parameters or the gate count. So we have applied certain approximations, like we have restricted the contractible orbitals of S to only the active orbitals. And then on top of that, we have added further approximations, which basically lowers down the gate consumption or the gate count as well as the parameter count. So here is a pictorial representation So as you can see that the arrow at the bottom basically tells about expressibility, and the arrow at the top tells about scaling. We can see that all our variants of the UICCSD and ANSAs, they have a scaling of the same order as that of UCCSD, but they have a much higher expressibility than the UCCSD ANSAs. So now we have run VQE with our UICCSD and ANSAs and its various approximations. And what we have seen that all of our ANSAs are capable of predicting energies up within tens of microhartree precision for the single reference region as well as the strongly correlated region. I mean, throughout the potential energy surface. But unlike the conventional UCCSD, where UCCSD does pretty well till geometries 1.75 angstrom, but it fails down for the geometries beyond that. So we can say that UICCSDN and its various variants are performing pretty well throughout the potential energy surface. And we have also plotted down the non-parallelity error corresponding to our ANSAs and the parameters requirement also. And on the left-hand side, I have mentioned the NPE in millihartree, and on the right-hand side, I have mentioned the parameters count. We can see that the parameters count for UCCSD is pretty low, but the NPE is very, very high. Whereas our least expressible ANSAs, which is the UICCSD and A pair ANSAs, that has a very, very low NPE with only additional few gates. So we can say that our ANSAs strikes the right balance between expressibility and the lower gate depth requirement. So I would like to conclude my talk by saying that the accuracy of the phase estimation is controlled by a predefined length of the phase beat. Inclusion of only the quasi-degenerate determinants in the reference state preparation scales down the computational cost without affecting the probability of the success. And our newly developed UICCSD and ANSAs spans the full wave function space, that too with least gate count in comparison to other traditional methods. So I would like to thank my supervisor and my collaborator, Dr. Srinivasa Prasanna, and my lab mates for this works, and thank you.
Thank you very much, Ms. Dipanjali, for a very nice talk. So any questions? Okay. Yes, Professor Sugisaki has a question.
Yes.
So thank you very much for very nice talk. I have a question about the first topic. I mean the IQPE after VQE.
Okay. Yes.
In your talk, in order to use the VQE wave function as a wave function in the IQPE, you don't have to. You don't have to fully optimize, but
sorry.
You don't have to fully optimize the wave function, but semi-optimized one is okay enough. But I think that in the real scenario, the VQE in the VQE total energy calculation or parameter optimization were performed with a finite number of measurements. So have you ever performed the VQE with finite number of measurements? I think this simulation was performed by using a scale vector simulator.
Sorry, I didn't understand your last line. Like finite number of measurements.
Yes,
Sorry, I
to
didn't get
calculate
that.
the energy.
Sorry.
To calculate the energy.
No, I actually didn't understand what is the meaning of finite number of measurements.
I mean that in the real, if we want to perform the VQE on real devices,
Okay.
you
Okay.
have to calculate the energy
Okay.
by finite sampling of the measurement outcome.
Okay. Okay.
But I think these simulations were performed by using state vector simulator.
Yes, using state
We
vector.
correspond to the infinite number of measurements to calculate the equation values. But in real devices, you cannot perform the infinite number of measurements. Instead of that, you only can do is the final number of measurements. So in that case, is because in such cases, optimizing the wave function completely is very difficult because of the statistical error. But I think that using this not fully optimized, but a semi-optimized wave function as an initial wave function in IQPE is possible by with the finite number of measurements. So my question is, have you ever performed the VQE simulation with the finite number of measurements or not?
No, we have done it using the state vector simulator.
Okay. So another question is about the VQE with only one excited case, only limited excitation operators.
Sorry, I didn't get it. Can you please repeat it once again?
Okay, so another question is about the VQE.
Yes.
With one excitation operator. Which correspond to two excitation from the Hartree-Fock state. Could you show me the result with the two configurations?
You're talking about this minimally parameterized answers?
Yes, yeah. Exactly. So in this case, the wave function includes only one parameter.
Yes.
So you can perform the optimization without using VQE, but fully classically. By I mean you can obtain the exact wave function within two active spaces, which correspond to MO1 and MO2.
Yes.
By diagonalizing the wave, the Hamiltonian matrix, which correspond to CAC SCF, sorry, CAC CI, with two electrons in two orbital cases.
Right.
So in that case, you don't have to perform the VQE. Instead of that, instead you can perform the exact wave function. You can obtain the exact wave function within these two electrons in two orbital space by performing CAC CI. So I think such approach is possible, especially in this, because this system is very small. So have you ever performed such computations?
What computation?
I mean the IQPE with the CAC CI two electrons in two orbital wave function as the initial wave function.
Yes, we can do that also. We can it's not necessary that we need to do a VQE in order to get this minimally parameterized state, true. But if we consider a larger system where the number of active orbital, I mean if the active orbital space is large enough, then maybe VQE will be of use.
Okay, thank you very much.
Sorry?
Thank you.
Oh, okay.
Okay, thank you. Are there any other questions? Okay, if not, then let's thank Ms. Dipanjali for a very nice talk.
Thank you. Thank you.
So thank you. Thank you very much. And thank you all for attending. Thank you.
Thank you. So shall I leave?
Hello, are you able to hear me?
Yeah. Shall
Oh,
I
yes,
leave?
yes.
Yeah.
Yes,
Okay.
please.
Thank
Yes,
you
please.
very much. Thank you.
Thank you very much. Thank you.